Good morning, one and all. Myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about the discussion on question bank. So, in this particular lecture, we are going to discuss how we will answer a short answer type questions and a long answer type questions, followed by analytical type questions. In what way we are going to express, and module 1, that is related to electrostatics questions and all, we will discuss in this particular lecture. So, state Coulomb's law. So, Coulomb's law states that the force between two stationary charges is directly proportional to the product of those two charges and is inversely proportional to the square of the distance between those two. That is given by Q1, Q2 by 4 pi epsilon naught. Sorry, Q1, Q2 by R square. Right? Where that proportionality constant is replaced by K, and that is given by means K into Q1, Q2 by R square, where proportionality constant K is given by 1 by 4 pi epsilon naught. As we know that epsilon naught value is equal to 8.854 into 10 power minus 12, or sometimes we may use this one is approximately equal to, that is 10 power minus 9 by 36 pi. Okay? So the force between two stationary charges is directly proportional to the product of those two and is inversely proportional to the square of the distance between two, is given by here the statement related to the Coulomb's law. Next, write the expression for Coulomb's law in vector form and explain the terms. So, suppose if you want to express the Coulomb's law in vector form, means that can be written as F is equal to Q1 Q2 by 4 pi epsilon naught R square into AR, where AR be the unit vector related to that one, and it is given by R by its magnitude. Then if you substitute in place of AR by this formula here, then F is equal to Q1 Q2 by 4 pi epsilon naught into modulus of R whole cube into R, where this R be the vector form. Right? R is the distance between the two point charges. Right? Suppose a point charge Q1 is located at particular and Q2 is located at particular, and the distance between these two are represented with R12. And from the origin, if you want to measure the distances, the help of position vectors as R1 and R2. So the distance vector is given by R12. Depending upon that, the Coulomb's law is to be expressed in terms of vector form, means this is the way we have to express. Then define unit vector. We are representing it with unit vector, means A suffix A is the notation for that, where A be the small a be the notation for the unit representation, and capital A be the vector notation. Suppose if we have a vector A like this, AX plus AY plus AZ, if you want to consider the vector A, then we will substitute here in place of A by this form, and unit vector can be defined as vector, it is the ratio of the vector to the its magnitude given by R by modulus of R, which is equal to AX plus AY plus AZ by root over AX square plus AY square plus AZ square. This is the definition for the unit vector. Specify the importance of divergence and Stokes theorems. Right? So, in order to analyze where divergence theorem is applicable for all the where the divergences exist in that particular, means can be states that closed surface integral S A dot ds is equal to integral V del dot A dV is for divergence theorem. And coming to the Stokes theorem, it can be given by closed line integral L A dot dl is equal to integral S del cross A dot ds. Means the divergence theorem gives us the relation between surface to volume integrals, whereas Stokes theorem gives the relation between line to surface integrals. If you close the surface, it becomes volume. If you close the line, then it becomes a surface. Then state Gauss law. So to define this Gauss law, the flux passing through any closed surface, which is represented with psi, is same as that of the net charge enclosed by that surface, is given by psi is equal to q enclosed, where the psi can be expressed as closed surface integral S d dot ds, means flux which is passing through any closed surface. So closed surface resembles closed line surface integral S d dot ds. So flux passing through a given area means it is represented with a density, then that is d dot ds is equal to charge enclosed, means integral v rho v dv. So if we close the line, then it becomes volume. So here we can consider the internal principle as or theorem as divergence theorem. Next, what is the first Maxwell's equation? So according to Gauss law, we will derive the first Maxwell's equation to be in electrostatic fields, that is closed surface integral S d dot ds is equal to integral v rho v dv is the integral form, or point form means by applying divergence theorem to this, then it becomes rho v equal to del dot d. Right? So if we express volume integral in terms of surface as integral v del dot del dot a dv, like that, then this rho v equal to del dot d can be written as point form or differential form of the Maxwell's equation for electrostatic fields. Next, list the applications of Gauss law. So when we are going to apply this Gauss law, means Gauss law is applicable for symmetrical charge distributions. So with the help of this, we can find for a point charge which is distributed in a spherical region, and for an infinite line of charge case, for an infinite sheet of charge case, and for a spherical region means the cross-sectional view of the coaxial cable case. So these are the different applications, means whatever the shape we have considered, whatever the imagination figure we considered, so throughout that the charge is to be uniformly distributed. That electrical charge is uniformly distributed. That is the case, Gauss law is applicable. Then define electric flux and give the relation between electric field intensity and electric flux density. Electric flux is represented with psi, and the flux, which is means electric flux, can be defined as electric lines of force. Generally, the flux is defined as lines of force, and electric flux means electric lines of force is said to be electric flux, and the relation between electric field intensity means it is represented with E bar, and electric flux density is represented with D bar. And the relation between two means D is equal to epsilon into E bar. Next, state the divergence theorem and give the expression. See, the flux passing through any closed surface is same as that of the net charge enclosed by that surface, and that is given by equation here. Closed surface integral S A dot ds is equal to integral V del dot A dv. So here A be the vector, and here del dot A be the divergence of a vector field represented with del dot A. Whereas it gives the relation between, means divergence theorem gives us the relation between surface to volume integrals. Next is state Stokes theorem and gives it expressions. So here also closed line integral L, and see line integral of any closed path is represented with L, that is closed line integral L A dot dl is equal to integral S del cross A dot ds, where del cross A bar represents curl of any vector field. So closed line integral L A dot dl is equal to integral S del cross A bar dot ds. So here divergence theorem gives us the relation between surface to volume integrals, and here it will be the Stokes theorem gives us the relation between line to surface integrals. Next, define electric potential. See, electric potential is nothing but electric voltage, and it is a potential difference between two reference nodes. That is given by, sometimes it might be defined as VAB. The potential difference between point A to B can be defined by here work done per unit charge when it is placed in a field called electric field. Hence, the name has given electric potential. Generally, it is represented with V equal to omega by Q. This electric potential in terms of field intensity is given by V equal to minus integral L E dot dV. So this negative sign represents us, means the field component, the work done, and the electric field intensity are opposite to the. The work is to be done by the external agent. It is represented with negative term. Then give the expression for the energy density for electrostatic fields. Generally, it is represented with W, energy. E stands for electrostatic fields, and the energy density in electrostatic fields is given by integral V d dot E dV, or integral V epsilon naught half into epsilon naught E square dV. Why? Because we know that the relation between D and E is D equal to epsilon into E. If we substitute D by here epsilon into E, then this becomes epsilon into E square D. And we are talking here epsilon naught means that is represented by the free space permittivity, and energy density for electrostatic fields is given by W equal to 1 by 2 integral V del dot E dV, or 1 by 2 integral V epsilon naught E square dV. Then define convection current density. Generally, there are three different types of current densities or exist. And in electrostatic fields, we have two current densities. One is convection current density, and another one is conduction current density. So here, convection current density doesn't require any medium to conduct, and it is to be considered, or it is to be given by here Jc equal to rho v into u, where rho v be the number of electrons in a given volume and U be the velocity of an electron. So convection current density is given by Jc is equal to rho v into U, and generally this Jc can be measured as ampere per meter square. Current per unit area, hence it is ampere per meter square. Next is define convection current density. So just now we have seen that is convection current density is represented with Jc, and it is given by rho v into U. So rho v be the volume charge density, and it is to be considered in a given volume, number of electrons in a given volume. Density is given by volume charge density, and U be the velocity of an electron. To produce this, it doesn't require any conducting medium, and in general it is to be measured in terms of ampere per meter square. Write the boundary conditions for conducting medium. So for the conducting medium case, in order to write the boundary conditions for conducting medium, we need to write first that between two dielectric media, what are the boundary conditions. So between two dielectric media, two boundary conditions are E1t equal to E2t, and D1n minus D2n is equal to rho s. If rho s is equal to 0, then D1n equal to D2n. Means tangential components of both the fields, medium 1 and medium 2, or electric field intensities are same for the dielectric between two dielectric medium. And here also D1n is equal to D2n means normal components of both the flux densities are continuous across the boundary case. If it is charge-free region, if rho s is equal to 0, D1n is equal to D2n. Right? And now we want to define boundary conditions for conducting medium. So for the conducting medium, inside the conductor there is no electric field. So for the conductors, we are assuming E equal to 0. Now if the conducting medium is assumed to be 0, there exists another medium called dielectric medium. So if we are assuming the medium 2Pa conducting medium, and E2t becomes 0, hence E1t equal to 0, or simply it is ET. Right? And this CT means this first medium is represented with dielectric medium. Right? Similarly for this, if you are assuming if E2t equal to 0, D2n is also 0. Why? Because for the medium 2 to be assumed as conducting medium, if E equal to 0, D is also 0. As we know that the relation between D and E is D equal to epsilon into E. If E is 0, D is also 0. Right? So for this also we can say that E equal to 0, E1t equal to 0, or simply Et equal to 0 is the one of the boundary condition, and another one is D1n or Dn is equal to 0, or sometimes it might be, if you consider in the presence of charge density, then D1n is equal to rho s, or we are assuming that if rho s is for a charge free regions, if rho s is equal to 0, D1n or Dn equal to 0. Right? So the boundary conditions for the two conducting medium given by here, Et equal to Dn is equal to 0, or sometimes Et equal to 0 and Dn is equal to rho s in the presence of charges and in the absence of charge density. Now define conduction current density. So in order to produce this conduction current density, it requires conducting medium. So upon applying the electric fields, then it is able to provide this such type of current densities are called conduction current densities, and it is represented by here Jc equal to sigma into E. So where sigma be the conductivity of the material and E be the applied electric field. Right? So Jc equal to sigma into E is also called as point form of Ohm's law. Right? Next, give the expression for the relaxation time. So to derive the expression for this relaxation time, we use the fundamental law of first Maxwell's equation to be derived for the electrostatic fields is Gauss law, and internally we are going to use the point form of Gauss law as rho v equal to del dot d. Right? So based upon this rho v equal to del dot d, we were going to derive the expression as Tr equal to epsilon by sigma, where epsilon be the permittivity of the material and sigma be the conductivity of the material. As we know that epsilon formula is epsilon equal to epsilon naught into epsilon r. Okay. So next, define Poisson's and Laplace's equations. Whereas Laplace's equation and Poisson's equations are to be interrelated, in order to derive these two also, we use the fundamental law called Gauss law. That is point form or differential form of Gauss law formula. If you consider rho v equal to del dot d, then from this the Poisson's equation is to be obtained as del square v equal to minus rho v by epsilon, and if you charge free regions case as a special case of Poisson's equation, if rho v equal to 0, del square v equal to 0 is said to be Laplace's equation. Next, what are the different types of capacitors, and give the C value for all. So different types of the capacitors. As we know that for a parallel plate, there are three cases of capacitors, capacitances we are going to we have learned in this particular modules. So that is given by here. For a parallel plate capacitor, C is defined as epsilon s by d, and there are three types of capacitors we have learnt, that is parallel plate capacitor, cylindrical capacitor, and a spherical type capacitor. Right? So for all the equations we need to write here. So C equal to epsilon s by d, and sometimes for a cylindrical type 2 pi a by 1 by a minus ln of b by a, and for the spherical type 2 pi a by 1 by a minus 1 by b, where a and b are the inner and outer spheres radiuses or radii. Then define polarization. So to define polarization, we need to represent it with capital P. Orientation of electric field in a particular volume is given by, or electric dipole moment per unit volume can be defined as polarization. Electric dipole moment per the unit volume is given by polarization, or in other words, we can define it as orientation of electric field that is to be vary in a particular point in a space with respect to the time t. This is what all the short answer questions which we are going to learn in this particular module 1 called Electrostatics. Next, coming to the long answer questions. So, state and explain Coulomb's law in vector form. So, first we will state the definition of a Coulomb's law, that is a force between two stationary charges. Let it be if you are assuming Q1 and Q2 are two stationary charges, and it is the force is directly proportional to the, or force between two is directly proportional to the product of these two and is inversely proportional to the square of the distance between these two, where that proportionality constant is replaced by k and its value is given as 1 by 4 pi epsilon naught. And in order to express this means the force or electric force is an example for a vector, means we need to express this one in terms of vector form. That's why mathematically we can state that equation as F is equal to Q1 Q2 by 4 pi epsilon naught R square into AR, where AR be the unit vector in the R direction. Okay, so this is what Coulomb's law. Now, if you want to express, suppose if you have 2-point charges, we will write the mathematical equation means F is equal to Q1 Q2 by 4 pi epsilon naught R square into AR. Instead of having 2-point charges, if we have n number of point charges and we want to locate all n number of point charges in a particular position, vectors called R12, R1, R2, R3 and so on, Rn, and based upon this, the force can be given by F is equal to Q by 4 pi epsilon naught summation of K equal to 1 to n Qk into R minus Rk by modulus of R minus Rk whole cube. Right? So if you substitute K by 1 to n numbers, then this is the approximated equation for the Coulomb's law in vector form. Right? So first we have to write a statement related to this for Coulomb's law. Then we need to write the vector form equation for the, if you have only 2-point charges, then instead of having only 2-point charges, if you have a number of point charges and we want to locate all a number of point charges at a particular position vectors as R1 to Rn, then we need to use superposition principle to express that Coulomb's law in vector form. So that is the case. Approximated equation is given by F equal to Q by 4 pi epsilon naught into summation of K equal to 1 to n Qk into R minus Rk by modulus of R minus Rk whole cube. Next, state and prove Gauss law. List the limitations of Gauss law. As we know that statement related to this Gauss law is the flux which is passing through any closed surface is same as that of the net charge enclosed by that surface. So to prove this, psi is equal to Q enclosed we need to consider, and this psi can be expressed as closed surface integral S d dot ds is equal to integral V rho V dV. Right? Now according to the divergence theorem, if you apply divergence theorem to the LHS part of this can be written as integral S d bar dot ds is equal to integral V del dot d bar into dv. Okay, so now if you observe here, the LHS as well as LHS part of 2 must be same. If LHS part is same means RHS part of these two must be same. From this we will write the equation as rho v equal to del dot d bar. This is called point form or differential form of the first Maxwell's equation to be derived in the case of Gauss law. Okay, and what are the limitations means whenever there does not exist any symmetrical charge distribution, that is the case, Gauss law is not applicable. Means if there exists a symmetrical charge distribution, whatever the imagination figure if you consider throughout that region, it will be, the charge will be uniformly distributed, then that is the case, Gauss law is applicable. Okay, next. Explain the following terms: homogeneous and isotropic medium and line surface and volume charge distributions. So depending upon the electrical properties like conductivity and permittivity and permeability, depending upon that, if the electric field intensity and electric flux density as linearly increases, then the type of medium is said to be homogeneous, and there exists a difference between two, then the type of medium is said to be isotropic type medium. Then coming to the line, surface and volume charge distributions. So line charge density is represent charge density is generally considered in terms of rho, and if you are talking about line, then it will be with rho L, or if you are talking about surface, then we need to return with the help of rho S, and if you are going to consider S with respect to volume, then it will be rho V, rho L, rho S, and rho V. So line, surface, and volume charge distributions are to be represented. Means for a line integral means integral L, rho L, dl. We have to consider this is the formula for Q, and for surface it is integral S, rho S, ds, and for volume it is integral V, rho V, dV. This is the way we can define all the charge distributions in the case of line, surface, and volume integrals. Next one is derive the boundary conditions for the tangential and normal components of electrostatic fields at the boundary between two dielectrics. So in order to derive the boundary conditions between two dielectric media means, suppose if you consider a boundary which is exist at z is equal to 0, means below z is equal to 0 we have medium 1, and above z equal to we have medium 2. So z less than 0 and z greater than 0. So z less than 0, medium 1 is exist, z greater than 0 to case medium 2 is to be exist. So depending upon these two, medium 1 and medium 2, those two can be considered as two dielectric medium. So for the two dielectric medium, in order to decompose or in order to consider the analogy between here, we need to use two Maxwell's equations, which are to be considered in the case of electrostatic fields. That is, first one is integral S d dot ds is equal to integral V rho V dV. This is the one of the Maxwell's equation for the electrostatics, which is derived from the Gauss law. And second one is closed line integral L E dot dl is equal to 0, and this is obtained from the relation between electric potential and electric field intensity. So in order to write the two boundary conditions, we need to use two Maxwell's equations, and this is applicable for all the lines, and this is applicable for all the surfaces. Based upon this analogy, we are going to consider here two boundary conditions as E1t equal to E2t and D1n is equal to D2n. From these two, we can say that tangential components of both the medium 1 and medium 2 are continuous across the boundary, and normal components of both the flux densities of medium 1 and medium 2 are continuous across the boundary. So tangential components of E are continuous means, and tangential components of D is discontinuous, and normal components of D is continuous means normal components of E is discontinuous across the boundary. This is the way we can write we can derive the boundary conditions for the tangential as well as normal components of electrostatic fields at the boundary between two dielectric medium or media. Next, obtain the expression for the capacitance of a coaxial capacitor. So to derive the equation for that, just we need to define first in general what is the definition for the capacitance, that is C equal to Q by V, and depending upon the shape type of the capacitor, if you evaluate, now we are going to write the equation for V as V equal to integral L E dot dl. Depending upon the length or surface or volume, we used to consider the notations as here I am using in terms of electric potential and electric field intensity relation, V equal to minus integral L E dot dl. So, and spherical case, we consider two types of the conductors as conductor 1 and conductor 2, where conductor 1 and conductor 2 respectively carries two types of the charges as plus Q and minus Q. Depending upon that, we will evaluate V equation and substitute this V by here, and to get the capacitance equation, that is C equal to 2 pi epsilon by ln of A by B. Okay, this is the equation for the capacitance of a coaxial capacitor. Okay, so in order to derive this one, we need to consider two concentric circles, and based upon this, this is the inner one means which is having the radius as A, outer one is having the radius as B. Depending upon that, the capacitance of a coaxial capacitor need to be derived as C equal to 2 pi epsilon A, epsilon by ln of A by B, or ln of B by A. So depending upon the shape, type of radius which we have considered for the inner one and outer one. Now derive the position of Poisson's and Laplace's equations and mention their applications. As we know that in order to derive the Laplace's and Poisson's equation, we need to know the one of the Maxwell's equation to be derived in the case of electrostatic fields using Gauss law as rho v equal to del dot d bar. And as we know, if you substitute d bar by epsilon into e bar, del dot epsilon into e bar, and if you consider here in place of e by, then the relation between electric field intensity and the electric flux density as E equal to minus del V, then from this, if you're going to write del square V equal to minus rho V by epsilon is called as Poisson's equation. And as a special case of this Poisson's law, if rho V equal to 0, then del square V equal to 0 is said to be Laplace's equation. And some of the applications of this Laplace's equation means in order to find the electric potential in the second order of the electric potential, we need to use Laplace's or either of the Poisson's equation. Next, explain the terms conduction current, convection current, and relaxation time. So, to derive, generally, to define conduction current, convection current, we need to know what actually current. So, current I can be defined as, or I is equal to Q by T. Charge per unit time or flow of electrons is said to be current, and in order to produce conduction current, it requires conducting medium, whereas the current which is flowing through an insulating material is an example for the convection current and relaxation time. To derive here the equations for these two current densities, we use for the convection current density Jc equal to rho v into u. For the conduction current density Jc equal to sigma into E. And similarly for relaxation time, in order to derive this, we use the point form of Gauss law, that is rho v equal to del dot d bar. Okay, so we can consider either in order to derive the equation for that, rho v equal to del dot d bar can be considered. Based upon this, we will derive the equation as T or Tr is equal to epsilon by sigma, where this relaxation time is also called as rearrangement time, and generally it is expressed in terms of seconds. Next is, what is the second Maxwell's equation, and give the relation between E and V. E is for electric field intensity and V be the electric potential. So second Maxwell's equation. So this is obtained from the closed line integral L E dot dl is equal to 0. Means according to the conservative nature of electrostatic field that can be exist, closed line integral L E dot dl is equal to 0 is called as integral form of second Maxwell's equation to be derived in electrostatic fields. Now by applying Stokes theorem to this, then from this we can write del cross E bar equal to 0 is called as point form or differential form of the Maxwell's equation, that is second Maxwell's equation for the electrostatic fields. And from this we will derive the relation between electric field intensity E and electric flux electric potential as V is E equal to minus del V is to be obtained. This is the point form, and integral form means V equal to minus integral L E dot dl. Right? So this is the relation between electric potential and electric field intensity. Next is, using Gauss law, derive expressions for electric field intensity and electric flux density due to an infinite sheet of charge, that is rho s. Right? So we can consider here now to derive the expressions for electric field intensity and electric flux density. We can use here Gauss law, that is flux passing through any closed surface S is same as that of the total charge enclosed by that surface is given by psi is equal to Q enclosed. So first we need to derive the equation for psi, and after that Q enclosed. By equating psi with Q enclosed, we are going to get the equation for E and D as D equal to, for the surface charge it is rho s by 2 into An, and electric field intensity E can be given by, that is rho s by 2 epsilon into A, where A and B the unit vector normal to that of surface. Right? So if you observe here, electric flux density due to surface charge and electric field intensity E due to surface, whereas difference is here. Electric flux density is independent of the medium and electric field intensity is dependent on the medium. Right? This is the way we can derive the expressions for electric field intensity and electric flux density using Gauss law with an application of infinite sheet of charge density case. Next, define conductivity and obtain the expression for continuity of current equation. So conductivity means, in general, it is represented with sigma. So conductivity means the device that exhibit electricity is the property that exhibit electricity is called as conductivity, and it is represented with sigma. And obtain an expression for the continuity of current equation. So to derive the expressions for continuity of current equation, we use again the point form or differential form of the Gauss law as rho v equal to del dot d bar. So if we simplify, or d bar, if you substitute here d bar by again del dot into epsilon into E bar and E by, so if you simplify or if you consider both sides integrations, differentiations and all, we are going to evaluate this one as the equation is to be obtained as del dot J is equal to minus rho v by epsilon. Del dot J is equal to minus rho v by epsilon is said to be continuity of current equation, or it is also called as simply continuity equation. Okay. Next, derive the expression for electric field intensity due to line charge. Now, to derive the expression for electric field intensity due to line charge, we need to define E related to, or first charge which is associated with the particular line charge density. The formula is Q is equal to integral L rho L dl. First, we need to consider rho L value and what is dl value. Then, if we substitute the Q value in this particular equation, means E is related to point charges, that is electric field intensity E can be expressed in terms of point charges, means E is equal to integral L Q by 4 pi epsilon naught R square into AR. So generally it is given as Q by, means that is Q by 4 pi epsilon naught into R square is the general equation. And if you substitute Q by this equation, it can be written as E equal to integral L rho L dl by 4 pi epsilon naught R square into AR. And based upon the figures and all, if you are assuming all the assumptions and substituted all the assumptions in this equation, it can be given by E equal to rho L by 2 pi epsilon naught rho into aero. Okay, so this is the way we can consider the formula for the electric field intensity E for the due to line charge. Generally, it is represented with charge is measured in coulombs, and the point charge means we are representing it with Q, and for line means it is represented with rho L. For surface it is rho S, and for volume it is rho V. So this is regarding line, means E is equal to rho L by 2 pi epsilon naught rho into aero need to be evaluated. Next, derive the expression for the electric field intensity due to surface charge. The similar analogy how we have evaluated all the assumptions, means related to this surface charge, first we need to define Q, that is Q equal to integral S rho S into ds. So this can be given by here, and if you substituted this Q value in E, that is Q by 4 pi epsilon naught R square into AR, and if you substitute Q by this formula, then E equal to integral S rho S ds by 4 pi epsilon naught R square into AR, right? So now depending upon the R direction, you consider the formula for ds, and after evaluating the R direction element and the distance, everything need to be substituted here. Then from that, we'll be getting the value or the final equation for that. Electric field intensity E due to surface charge is given by E bar equal to rho s by 2 epsilon naught into A. Okay, this is the way we have to derive the equation for the electric field intensity due to the surface charge. Next, derive the expression for electric field intensity due to the volume charge. So how we have evaluated in the previous case, similarly here also, first we need to define Q, that is Q equal to integral V rho V dV. Why? Because it is related to volume charge, then Q must be given as like this. And E can be expressed as Q by 4 pi epsilon naught R square into AR. And if we substitute Q by this thing, then integral V rho V dV by 4 pi epsilon naught R square into AR. Like this, if we evaluate, this equation need to be obtained as E equal to, that is rho V means rho V into 4/3 pi AQ, right? So this is the way the equation for electric field intensity due to volume charge need to be obtained. That is Q by 4 pi epsilon naught R square into AR to be evaluated for this particular volume charge. Then state Gauss law using Divergence Theorem and Gauss law, relate the displacement current density D and the volume charge density, right? So Gauss law, psi is equal to integral S d dot ds, and Q enclosed is equal to integral V rho V dV, and the relation between the psi and Q means the flux passing through any electric flux passing through any closed surface is equal to the total charge enclosed by that surface. Now depending upon that, psi is equal to Q enclosed, and if you equate those two, closed surface integral S d dot ds is equal to integral V rho V dV. By applying proper divergence theorem to that Gauss law, then it becomes rho V equal to del dot d bar, where rho V be the volume charge density and del dot d bar be the divergence of electric flux density, right? So next one is derive the expressions for the capacitance of a parallel plate capacitor. So first we need to define in general capacitance equation. C is equal to Q by V. Now from this V can be evaluated, that is integral L E dot dl. After evaluating this thing, we substituted here for a parallel plate capacitor, then it can be given by epsilon S by D, where epsilon be the permittivity which is exists between the or the between the two conductors, and S be the plate separation area, and small d be the distance between two conductors. So for a parallel plate capacitors means it is having two conductors, where two conductors are having the same magnitudes as carries plus q and minus q, and the directions in which they are placing are in different directions. Based upon that, for a parallel plate capacitor, C can be given by here epsilon S by D. Next is derive the expression for energy density in electrostatic fields. So in order to derive the expression for energy density in electrostatic fields, first we need to define the amount of work done in order to assemble all the point charges in the one infinity region to the some specified particular region. Depending upon that, the total energy equation is to be placed. There we are assuming two types of the point charges, W1, W2, W3. So in order to assemble the first point charge Q1, then energy or work done required is considered to be as W1. For the point charge 2, W2, and for the third one it is W3. And if you are placing the three charges in the reverse order, and by adding these two conditions and by applying proper divergence theorem and integrations formulas under evaluating everything, then energy density in electrostatic fields is to be derived as WE equal to half integral V epsilon E square dV or half integral V d dot E dV. Okay, this is the way we can derive the energy density in electrostatic fields. Next, obtain the expression for the capacitance for a spherical capacitor. So, consider one sphere of radius, inner sphere and outer sphere, which is having the radius as A, and outer sphere is having the radius as B. And here throughout this negative charge is carrying, throughout the sphere plus Q is charging, and the difference between these two is given as the separation is with the epsilon. Based upon this, if you consider first definition as C is equal to Q by V, and if you evaluate the V value, that is integral L E dot dl, then after substituting V into this, then Q can be defined as here 2 pi epsilon by 1 by A minus 1 by B, right? So for a Earth to be considered as a sphere, outer sphere radius need to be infinity, and something by means V tends to infinity, then V tends to infinity, this becomes 0. That is the case C equal to 2 pi epsilon A need to be evaluated. Next, explain conduction current and derive the expression for the conduction current density. So to derive the conduction current density, it requires conducting medium. By applying proper electric field to that, then it is to be derived, that is called as Jc equal to sigma into E. Then sigma be the conductivity of the material and E be the applied electric field. So this is also called as point form of Ohm's law. Point form of Ohm's law. How it is analogous to Ohm's law means, according to V equal to IR, where V is analogous to E in that, and I be the Jc and R be the sigma. So this is the way we can equate the point form of Ohm's law into normal Ohm's law, and the conduction equation for conduction current density, that is J equal to sigma into E, is called as point form of Ohm's law. Next, convection current density. So that is given by, again, depending upon the currents densities we are going to use in this particular electrostatics. We have two types of the current densities. One is convection current density and another one is conduction current density. Whereas convection current density doesn't require any conducting medium, then in this case the J can be given by rho V into U, where rho V be the volume charge density and U be the velocity of an electron. Next, state Gauss law and obtain the first Maxwell's equation for the electrostatic fields. So as we know that Gauss law, the flux passing through any closed surface means, this is the, if you consider one closed area, then the flux lines which is passing through a given area, and inside the flux and outside the volume must be same. So psi is equal to Q enclosed. The flux passing through any closed surface is same as that of the net charge enclosed by that, and by applying proper divergence theorem to that, then rho V equal to del dot D bar is called as point form or differential form of Maxwell's equation to be derived for the electrostatic fields. Okay, rho V equal to del dot D bar. Rho V is nothing but volume charge density, and del dot D bar can be considered as a divergence of electric flux density. Next, coming to the analytical questions which are exist in the electrostatic fields, that is, first, a point charges 1 millicoulombs and minus 2 millicoulombs are located at 3, 2, minus 1 and minus 1, minus 1, 4 respectively. Calculate the electric force on a 10 nanocoulombs charge located at 0, 3, 1 and electric field intensity at this particular point we need to evaluate. So first of all, given data, given one is equal to Q1 equal to 1 millicoulombs, Q2 equal to minus 10 millicoulombs, and the respectively Q1 and Q2 are located at R1 equal to 3, 2, minus 1 and R2 equal to minus 1, minus 1, 4. Right? And calculate the electric force on a charge. Q is given, that is 10 nanocoulombs, and this Q is located at a particular distance R is given by 0, 3, 1. So first we need to find electric force. The formula is here, F is equal to Q1 Q2 by 4 pi epsilon naught R square into AR, or in general this force F is given by, for an endpoint charges case, Q by 4 pi epsilon naught into summation of K equal to 1 to N Qk by R minus Rk whole cube into R minus Rk. Right? So if you substitute K by 1 and 2, then Q by 4 pi epsilon naught Q1 by Q1 into R minus R1 by R minus R1 whole cube plus Q2 into R minus R2 by modulus of R minus R2 whole cube. Right? So as we have Q1, Q2 as 1 milli and minus 2 milli, R1, R2 are 3 to minus 1 and minus 1, 4, and Q is 10 nanocoulombs and R is 3, 0, 3, 1, and everything is supposed to substitute, and finally the F need to be obtained in a vector form. Right? So similarly, after getting this F value, we need to find electric field intensity at that particular point. Means, as we know that electric field intensity vector E in terms of this equation is E equal to F by Q. Force per unit charge is given by electric field intensity. After getting this F value, you just substitute in place of F by this one and Q by 10 nanocoulombs. Then E vector need to be obtained. And this F is generally measured in newtons and E is Newton per coulomb or simply volts per meter. Okay. And in order to substitute 1 by 4 pi epsilon naught. So if you substitute epsilon naught by 8.854 into 10 power minus 12 or else, which is approximately equal to 10 power minus 9 by 36 pi, or 1 by 4 pi epsilon naught means we use the notation as 9 into 10 power 9 meters per second. Farad is for the value just to be considered as in place of 1 by 4 pi epsilon naught by 9 into 10 power 9. Right? This is the way we have to evaluate first electric force on a particular charge, that is 10 nanocoulombs, and from that we will evaluate electric field intensity at this particular one. Next, again, point charges 5 nanocoulombs and minus 2 nanocoulombs are located at 2, 0, 4 and minus 3, 0, 5 respectively. Then calculate the electric force on a 1 nanocoulomb point charge located at minus 1, 3, 1 minus 3, 7 and electric field intensity E at 1, minus 3, 7. So generally this first of all we need to identify what is the given one. Means Q1 is equal to 5 nanocoulombs and Q2 equal to minus 2 nanocoulombs, and this thing R1 is given as 204 and R2 is minus 305. Then here Q value is given as 1 nanocoulomb and this is the one which is particularly for R 1 minus 3 7. So as we know that the formula for the electric force, that is Q by 4 pi epsilon naught summation of K equal to 1 to N Qk into R minus Rk by modulus of R minus Rk whole cube. Right? So substitute all these things in this, then you're going to get the value of F in terms of measured in newtons. And as we know that 1 by 4 pi epsilon naught value, it is approximately equal to 9 into 10 power 9. Okay. So everything need to be substituted. Then we substitute K by 1 and 2. It becomes Q1 into R minus R1 by R minus R1 whole cube Then R, if you substitute K by 2, R minus R2 by R minus R2 whole cube. Then after simplification, everything, then F is to be measured in terms of newtons. After getting the value of F, we'll be finding the electric field intensity E at this particular 1, minus 3, 7. Okay. And generally, this electric field intensity vector E is to be measured in volts per meter, or according to the formula Newton per Coulomb. Okay. Then third one, determine D at 4, 0, 3 if there is a point charge minus 5 millicoulombs at 4, 0, 0 and a line charge minus 3 millicoulomb per meter along the y-axis. Okay. So if you have an axis called along x, y and z, and D we need to find at particular point D at 4, 0, 3 if there is a point charge of, means a point charge is located at, suppose if you are assuming the point charge is located at x-axis, and that is at minus 5 millicoulombs, and a line charge is along the y-axis. Here rho L need to be exist, right? So now total flux density D need to be measured as D equal to dq plus dl. dq can be written as, in general, E is to be given by E is equal to, or D equal to, that is q by 4 pi r square into AR, q by 4 pi r square into AR. So r square means where is the, it is the distance between 4032, r is in one case, and 4032, 400 for the line charge case. So separately if you evaluate, and dl if you evaluate that one as rho L by 2 pi rho into A rho is the another formula. So if you substitute all the values in this and this, then you're going to get D in terms of this thing, vector form, and it is to be measured in terms of Coulomb per meter square. Electric flux is generally measured in coulombs, and occupying some area means we need to measure in terms of density as Coulomb per meter square. Right? So flux density due to point charge as well as line charge density, and it is to be measured in terms of Coulomb per meter square. Next, 2 point charges minus 4 microcoulombs and 5 microcoulombs are located at 2, minus 1, 3 and 0, 4, minus 2 respectively. Find the potential at 1, 0, 1 by assuming zero potential at infinity. So 2 point charges means Q1 is given, Q2 is given, and R1 is given as 2, minus 1, 3 and R2 is 0, 4, minus 2. So R1 need to be written as here 2, minus 1, 3, or this R1 is also able to write as 2AX minus AY plus 3AZ. And similarly R2 can be 0, 4, minus 2 can be given by 4AY minus 2AZ. And find the potential at this particular. So as we know that V is given by, that is W by Q, or work done per unit charges, or the potential difference between these two means VAB can be considered to be as VA minus VB, and those two are given by VA is nothing but Q1 to the potential at point A to the potential at point B, and the distance between two are need to be considered as, means Q by 4 pi epsilon naught into R minus R1 Q1 minus Q2 by 4 pi epsilon naught into R minus R2, where Q1, Q2 values are given. R value is 1, 0, 1 and R1 is 2, minus 1, 3, R2 is 0, 4, 2. And we know that 1 by 4 pi epsilon naught value need to be as 9 into 10 power 9. And substitute everything in this equation, then PAB need to be obtained, and generally it is to be measured in terms of voltages. Okay. Then 101 can be written as R means is given by 1, 0, 1 which is equal to AX plus AZ. Right? So the points are given. We need to write in terms of vectors. Vector form can be written in terms of two different ways. One is with all the magnitude terms, or along with the magnitudes, we need to write unit vectors also. Right? Depending upon this, the potential need to be evaluated and it is to be measured in terms of volts. Next, a cylindrical capacitor has a radii A equal to 1 centimeter and B equal to 2.5 centimeters. If the space between the plates is filled with an inhomogeneous dielectric with epsilon r equal to 10 plus rho by rho, where rho is in centimeters. Find the capacitance per the meter of the capacitor. For a cylindrical capacitor, the formula is given by 2 pi epsilon by ln of B by A. 2 pi epsilon by ln of B by A, where 2 pi into epsilon is given by here. In general, it is given as epsilon naught into it. Epsilon is generally written as epsilon naught into epsilon r, and which is equal to epsilon naught into epsilon r is given by 10 plus rho by rho. And substitute in place of this thing by 2 pi epsilon naught into 10 plus rho by rho y and ln of B by A. B value is 2.5 centimeters into 10 power minus 2 by 1 centimeter, 1 into 10 power minus 2. So like this, if you evaluate, and epsilon naught value by, we will consider it as 8.854 into 10 power minus 12, or which is approximately equal to 10 power minus 9 10 power minus 9 by 36 pi. We consider its value as epsilon naught. Now, and everything need to be substituted over here, then capacitance C need to be obtained. As the capacitance is to be measured in terms of farads, and the resultant one is to be expressed in terms of farads. Right? So the two radius values are given, A equal to 1 centimeter and B equal to 2.5 centimeters. And along with that, epsilon r value is given as 10 plus rho by rho. And in the denominator or in the formula itself, we'll be having C equal to 2 pi epsilon by ln of P by A. And as we know that epsilon means permittivity of the material is to be considered as the product of free space permittivity and relative permittivity. So finally, the capacitance, whatever the value which is to be obtained, is to be measured in terms of farads. Next, 3-point charges, 2 microcoulombs, 4 microcoulombs and 8 microcoulombs are located at 0, 0, 0, 0, 0, 0, 1 and 1, 0, 0 respectively. Find energy in the system. So 3-point charges means Q1, Q2 and Q3 need to be given, and R1, R2, R3 are to be given. So here R1 is to be given as 0, 0, 0 means total is equal to 0, and R2 is AZ, R3 is AX need to be expressed. And energy can be given by here, work done per unit charge. W equal to, generally the potential is given as work done per unit charge, and work done we need to multiply, energy we need to calculate means V into Q can be considered. Okay, so VAB and VBC, similarly VCA can be calculated. From 1 to 2, 2 to 3 and 3 to 1 we need to consider here. So work done in order to assemble 3-point charges means that is the case W equal to W1 plus W2 plus W3. So it is given by Q1 into V1 plus Q2 into V12 plus V13 plus Q3 into V23 plus V31 plus V32. Right? So this is the way we can evaluate the total energy present in the particular system. So Q1 into V1 means in order to find this, the potential and direct values need to be substituted as Q1, Q2, Q3 by 2, 4 and 8 micro, and followed by, in order to find the distances here, V1 value as directly R by R value means that is, and if you want to find the value of V12, it is the potential difference between V2 to V1, and V13 can be written as V3 minus V1. Similarly, V31 is V1 minus V3, and V32 is V2 minus V3, right? So this is the way we have evaluated all the potentials, and we need to substitute it in this particular one. And finally, whatever the value which is to be obtained in the case of work done or energy, this can be measured in terms of joules. Okay, next. Given that D equal to Z cos square phi Az Coulomb per meter square, and calculate the charge density at 1, pi by 4, 3, and the total charge enclosed by the cylinder of radius 1 meter with -2 is less than or equal to Z is less than or equal to 2 meters. So here D value is given, that is Z cos square phi Az Coulomb per meter square, and the charge density we need to evaluate. And there is a direct relation between rho v charge density to the flux density as rho v equal to del dot d bar. So divergence of this thing is given, and rho phi z values are given, means cylindrical coordinate system variables are given. Based upon that, we need to identify the differential components as d rho, rho d phi and dz. Depending upon that, we will be writing the divergence of flux density as d, and finally it should be expressed in terms of some coefficients which are exist in the given one as z, phi and rho. Then in that case, we just substitute rho by 1 and phi by pi by 4 and z by 3, right? So this is the way we have to get the value for charge density as rho v equal to del dot d bar, and the total charge enclosed by the cylinder of radius. After finding this rho v, charge enclosed means Q enclosed is equal to integral v rho v dv is the general formula. So to find this integral v means 3 times integration we need to consider. So rho equal to, phi equal to, z equal to. Rho equal to 0 to 1 meter, and phi equal to 0 to 2 pi, and z is equal to -2 to 2, and substitute whatever the rho value which is getting from here to here, and dv is nothing but rho d phi dz. So finally, whatever the value need to be obtained, that should be measured in terms of coulombs. Okay, so this is the way we have to evaluate. If the flux density value is given, from the flux density, how to evaluate volume charge density, from the volume charge density, how to evaluate total charge which is enclosed by that cylinder. Next, for the current density J, 10Z sine square phi aero ampere per meter square is given. Find the current through the cylinder surface, that is rho equal to 2. So current we need to find, and current density is given. That the formula current in terms of current density means I is equal to integral S J dot ds. Then substitute integral S means we are supposed to integrate this one with respect to 2 variables, and the 2 variables are need to be given as a rho means differential components are d rho, rho d phi and dz. Rho direction is given, means the formula for ds is equal to rho d phi dz. Hence phi is equal to 0 to 2 pi and z is equal to 1 to phi, and substitute j by 10z sine square phi aero dot rho d phi dz aero. As we know that aero dot aero value is 1, then after simplification and substituting limits by phi equal to 0 to 2 pi and z is equal to 1 to phi, the current value need to be obtained, and it is to be measured in terms of amperes. Next, 3-point charges and same 5 microcoulombs, 8 microcoulombs and 2 microcoulombs are located at these 3 points, means Q1, Q2, Q3 are to be given. R1, R2 and R3 values are given. Energy we need to find. So the total energy not to find, we need to find first the energy in order to assemble or the work done in order to assemble Q1, then Q2 and Q3 need to be written. So which is equal to Q1 V1 plus Q2 into V12 plus V13 plus Q3 into V31 plus V32. So the potentials in order to assemble or the work done in order to assemble the charge Q2 from 1 to 2 and 1 to 3. Similarly, in order to assemble charge Q3 from 2 to 3 and 1 to 3. This is the way we have to evaluate, and totally we need to express total energy in order to find all the energy which is exist in this particular one is to be measured in terms of joules. Next, if D equal to 2y square plus z into ax plus 4xy into ay plus xz into x into az Coulomb per meter square is given, volume charge density we need to find. And rho v in terms of volume charge density, that is rho v equal to del dot d bar, and substitute in place of d bar by dx ax dy ay dz az, then d vector is given, we need to substitute, and finally all in terms of x y z values by x equal to -1, y equal to 0, z equal to 3. Then you're going to get volume charge density. Then after that, flux through the cube defined by means psi we need to find. Psi is equal to integral s d dot ds. And to find the value here, now to write the equation for ds, flux through cube defined by means this closed surface integral is d dot ds. This can be written as integral xy x2y d dot dx dy az plus integral y to z d bar into dy dz into ax plus integral z to x d bar into dz dx into ay. So like this, if you evaluate the flux which is passing through the cube defined by flux, psi can be obtained, and it is to be measured in terms of coulombs. Similarly, the total charge enclosed means q enclosed is equal to integral v rho v dv. See, according to the Gauss law, this flux passing through any closed surface and charge enclosed must be same. And this is the case, you're supposed to get the same one. Psi is equal to Q enclosed is equal to, it is to be measured in terms of coulombs. Right? So these are the different types of short answer as well as long answer, and some of the analytical questions which are to be covered in electrostatic fields. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.